All right, welcome everyone to our week 4 recap. Again, in this week we were covering 3.1 through 3.5. And as I look through your responses to our participation survey, the main categories that I see are the mean value theorem or Rolle's theorem. I see stuff, a good amount about curve sketching and horizontal asymptotes or slant asymptotes. I also saw a few about critical numbers or figuring out where a function's increasing or decreasing, things like this. So I've chosen 4 problems that I think hit a good sampling of those items. In reality, right, example number 4 down here, this is going to be our curve sketching problem from 3.5. You'll notice that, right, it has the asymptotes in there, so slant, vertical, horizontal asymptotes, we'll talk about it all. Even, odd, or neither. Critical points, so again, we're going to practice getting some critical points and figure out where that's increasing, decreasing. Inflection points, and of course we're going to use that all to get a sketch of the graph. So really these curve sketching problems have embedded in them a lot of the other sections, the increasing, decreasing, the asymptotes, all that sort of stuff. Now I did give another problem here about finding critical points. And then we also have 2 problems about, well, one's the Rolle's theorem and one's the mean value theorem. So again, I'm going to go through all of these problems in this video. If you're not interested in all of them, you just scroll and figure out, if you only want to see examples 2 and 4, just watch examples 2 and 4. But yeah, this will probably be a decently long video thanks to example number 4. These are usually longer problems. So let's go ahead and get started. All right, so for example number 1, we just want to find the critical points. So we have to remember the definition for the critical points are wherever the derivative is equal to 0 or the derivative is undefined, and remember those critical points, they need to be in the domain of the function. And the point is in the domain of f. So I guess even before we start here, let's kind of think about this side algebra problem, right? In order for it to be in the domain of f. So remember back in our algebra days, the way that we figured out the domain is really we listed the things that weren't in the domain. Right? And kind of everything that's not in the domain is therefore in the domain. So the things that you have to watch out for when you're looking for a domain, right? These are things like dividing by 0 or taking negative square roots, things like this. Right? So in this case, if I look at my function over here, I don't see any division. So I really don't have to worry about dividing by 0 in this case, but I do see a square root. And so that's got me kind of concerned. Right? So okay, I don't want to put negatives in that square root. So if you don't want to put negatives in that square root, well, let's isolate the piece that you're actually plugging into the square root, 10 minus t. So 10 minus t. And if I don't want to plug in negatives, that's to say that I want this to be greater than or equal to 0. Right? If it was less than 0, that would be a negative number that I was plugging into the square root. The square root of a negative number isn't real, and thank goodness we're not doing, imaginary or complex calculus. It does exist, it is out there, but luckily we're just doing real valued calculus, so we're going to stick with the real numbers here. All right, so all that to be said, right, this means that if I go ahead and rearrange my inequality, this means that t needs to be less than or equal to 10. We'll check our answer at the end of this problem, and basically this will come down to, you'll see that there's no picture, there's no graph when t is greater than 10. So the only places that we're going to be looking for critical points, right, is when t is less than or equal to 10. Alright, so there's kind of the algebra stuff. Now let's go over here and write these 2 statements have to do with the derivative. So we need to be able to take the derivative of this function. So let's go ahead and start with that. In order to take the derivative of this function, we can see really that this is a function t. Oops, let me go ahead, zoom out here. This is a function t times a function the square root of 10 minus t. So even putting in this dot right here really shows that, hey, we're going to have to use the product rule here. Right? This is a product of two functions. So let's go ahead and calculate out the derivative. F prime of t is equal to the derivative of the first, well, the derivative of t is just 1, times the second, plus the first, times the derivative of the second. And here you may even want to rewrite this instead of the square root. We could rewrite this as raised to the 1/2 power. Right? So that's showing that I'm really going to be using the power rule here. So okay, if I want to take the derivative of this, the 1/2 is going to come down. We're going to have 10 minus t inside, reduce my power by 1, and then don't forget about the chain rule, right? The chain rule says take the derivative of the outside function. The outside function is, hey, stuff's being raised to the 1/2 power. So you take the derivative of that, leave the inside alone. That's why the 10 minus t didn't change at all. Then you multiply by the derivative of the inside, and the derivative of the inside is going to be -1. Right? So the derivative of 10 minus t is -1. All right. So now this looks a little bit messy. Let's take a few lines to clean this up. 1 times anything is just itself. And let's see. We have this -1. So instead of adding, let me go ahead and do subtraction here. And let's put all the things in the denominator kind of together and all the things in the numerator together. So there's a t and a 1 in the numerator, so that's just going to be t. In the denominator there's a 2 from the 1/2 here. And also remember, whenever you have an exponent, right, a negative exponent, this is the same thing as dividing by. So dividing by 10 minus t to the positive 1/2. Right? So that negative exponent, you can push that into the denominator and use up that negative sign. All right, and then let me go ahead and rewrite this. Instead of that 1/2 power, let's go ahead and use the square root notation, right? Because that gives us a better idea of what's going on here. All right, and then finally, we'll see there's a couple of different ways that you could go with this, but we'll see that this simplifies a lot if I get a common denominator. So, okay, because again, there's kind of two fractions. They want to be able to talk to each other. We want to be able to relay information between them. So let's go ahead. I'm going to put a 2 root of 10 minus t, right? That's the denominator over here. Of course, if I put one in the denominator, I should also put one in the numerator. So 2 root 10 minus t. That way I haven't changed anything mathematically. So okay, let's go ahead and simplify. Now it's all over one denominator, 2 root 10 minus t. And then in the numerator, let's see, well, I have this root 10 minus t times root 10 minus t, so that's root 10 minus t squared. So that square root's perfectly going to go away. And I'm just going to have, well, 10 minus t. And it looks like I have minus another t. I can go ahead and distribute that 2 to each piece here. And so finally I'm going to get 20 minus, and let's see, that would be negative 2t minus another t, so that's going to be minus 3t. All right, so here's what my denominator, this is what my derivative simplifies down to. All right, so now let's go back up here. Remember, what were we doing with all of this? Well, we were trying to figure out, 1, where is the derivative equal to 0? Or 2, when is the derivative undefined? Because that's where we're going to get critical points. Again, assuming that this is in our domain. So let's go ahead and deal with 1 really quick. When is that derivative equal to 0? So we have 20 minus 3t divided by 2 root 10 minus t. When is that equal to 0? So I could go ahead and cross multiply. Right? Take that denominator, cross multiply up here. Well, 0 times anything is just going to be 0. So this is just going to give me 0 is equal to 20 minus 3t. Let's go ahead and subtract or add 3t to both sides. So I'm going to get 20 is equal to 3t. Then I could go ahead and divide by 3, and I get t is equal to 20/3. So remember, 21/3 is right around 7. 21/3 is right around 7. So this is a little bit less than 7. Because again, we have to make sure that we're in the domain of the function. So is 7 or something a little bit less than 7 less than 10? Yes, absolutely. So this is actually going to refer to a critical point. All right, so that's where the derivative is equal to 0. What would it take for the derivative to be undefined? And quite often we're asking the same sort of questions here about the derivative now. They were asking about the original function, right? We called that domain for the original function. Here we're just asking where is this undefined, right? So, okay, the places where it's undefined is where you're dividing by 0 or where you're taking, a negative in the square root, things like this. So we can see there's actually a couple things to deal with. We do have a square root, so we want to make sure the thing that we're plugging into the square root, right, should be greater than or equal to 0. And this just tells us again that, well, t should be less than or equal to 10. Okay, but that's what we already needed for it to be in the domain. So that's not really any new information here, right? So this is one place where the derivative would be undefined when t is greater than 10, right? And it's because, right, the function's not defined there. So again, not so much new information. So that's the square root stuff. But here in the derivative, we also see that we have division, right? We have division. And so we want to make sure that we're not dividing by 0, right? So, okay, if we were dividing by 0, then this would be undefined. That's a point of interest, right? So, okay, what would it take for us to divide by 0? Well, our denominator would have to be equal to 0. Well, I could go ahead and divide by 2. I could square both sides. And then I can move the t to the other side. So when t is equal to 10, we have that this square root would be equal to 0, and we'd be dividing by 0. So this is a place, again, where the derivative is undefined. Now, is this in the domain? If I go back over here, the domain is all the places where t is less than or equal to 10. So it is in the domain, right? Because it's less than or equal to, in particular, equal to 10. So we have two critical points here. We're going to have one associated when t is equal to 20/3, again, right around 7. And we have another critical point when t is equal to 10. Alright, so let's go ahead and check our work, kind of how these things appear. And I went ahead and I'm using the Desmos grapher here. And I went ahead and I graphed our function, right? So we have this t times the square root of 10 minus t. And we can go over here and we can see right up here, around 6.667, a little bit less than 7, right, we actually have a maximum, a place where the derivative is equal to 0, right? If we had a nice tangent line here, it would be a horizontal tangent line. So this is one place where we have a critical point. The other place where we have a critical point is over here at 10. You can see that, again, when t is greater than 10, this doesn't make any sense. We would be plugging negatives into the square roots, and so we don't get any picture for our function. However, when it's less than 10, like we have here, right, we actually get, a nice picture. Now, when it's equal to 10, this is a place where it seems to have a vertical tangent line, right? It's coming in very, very steep here. So at 10, if you were to ask what is the derivative, or the one-sided derivative, the answer would be that it's undefined. And so that's why we have critical points at these two values, 6.667, or that's going to be our 20/3, and at 10. All right, so again, it's nice to do a graph like this just so that way we can see what are we doing with all of this algebra and this calculus, right, manipulating all of these functions algebraically. It's nice to put a graph to this to see what have we actually done. Alright, so this was a little bit longer. Examples 2 and 3 we'll be able to go through a bit faster. So example 2, consider this function on an interval, right? So the interval is, I guess, -6 to 1 down here. Find the c-values that satisfy the conclusion of Rolle's theorem. So Rolle's theorem says, right, if you have a nice continuous and differentiable function on your interval, then you can go out and find a place where the derivative is equal to 0. And we have some extra condition. And that is so long as the function's value on the endpoints is the same. So that is, let's go ahead and check and make sure that this satisfies the hypotheses for Rolle's theorem. Let's check out what is f of -6 and what is f of 1. So maybe I'll go ahead and do f of 1 first. So here's my function. I'm plugging in 1 everywhere I see an x. I get 1 plus 5 plus -6. So that's just going to be 0. Okay, fine. How about f of negative 6? Well, when I take negative 6 and I square it, I'm going to get positive 36. When I take negative 6 and I multiply it by 5, I'm going to get negative 30. And when just subtract away 6. So I get 36 minus 30 minus 6, so that is again equal to 0. So here you can see that the function's value at negative 6 is actually the same as the function's value at 1. Now, our function is nice, it's continuous and differentiable actually everywhere because it's just a nice quadratic, right? It's a polynomial. So these are going to be continuous and differentiable everywhere. So this satisfies all of the conditions for Rolle's theorem. These are all the things that we need to have hold true. And then, so in this case, Rolle's theorem says, right, the conclusion of Rolle's theorem is that you can go out and find a c value, at least 1, where the derivative at c is equal to 0. So we can go ahead, calculate out the derivative of our function. So our derivative is going to be 2x plus 5. And we want the derivative at c. So instead of maybe f prime of x, I'm going to do f prime of c. So I'm just going to do c here instead of x. And now we can go ahead and solve. So I can go ahead and subtract 5 from both sides and divide by 2. So our conclusion here is c is equal to negative 5/2. And the big thing here is that is within our interval, right? So our interval is from negative 6 to 1. That c value is inside of that interval. So in this case, there's only one c value that satisfies the conclusion of Rolle's theorem, and this is it. It's c equals negative 5/2. All right, Rolle's theorem is a special case, a special situation for the mean value theorem. So let's go ahead and look at the mean value theorem and see how these kind of relate. So example number 3, I have a nice picture of a graph here. I guess it's some g of x. And I would like to find c values, right, that satisfy the conclusion of the mean value theorem on the interval from 2 to 8. So our interval of interest here is from 2 all the way to 8. I guess the function's value at 2 is up here at 3. And the function's value at 8 is all the way up here. It looks like this is at 9. So let's remind ourselves really quick what the mean value theorem says. The conditions for the mean value theorem, right, is that you need it to be continuous and differentiable on that interval. So in this case, our interval is 2 to 8. So it needs to be continuous on 2 to 8, and it also needs to be differentiable. And technically, you can reduce down, and you only need the open interval here for differentiability. So that's all very technical, but let's make sure that these conditions are met. So let's go over to my graph here, and let's see, continuous, right? If I was to sketch this by hand, are there any places where I would have to do a jump, right? There were different types of discontinuities. There were jump discontinuities, there were removable discontinuities, there were vertical asymptotes, or infinite discontinuities, right? But I don't see any of those in my picture. So it looks like it is continuous. What about differentiable, right? How can a function not be differentiable? And remember, there were things like, well, if it's not continuous, it's not going to be differentiable. If you have a vertical tangent, it won't be differentiable. Or if you have one of these jagged edges, right? And as I look here, I don't see any places where you would have a vertical tangent. I don't see any jagged edges. It's not discontinuous any place. So yes, it is going to be differentiable as well. So these are the big conditions for the mean value theorem. And remember, if these things hold true, then the mean value theorem's conclusion says this, that you can go out and find a c value, so that way the derivative at c is equal to the average rate of change. It just says that the function's derivative here, or its instantaneous rate of change, will be equal to the average rate of change, at least at one place. Right? So if we were to calculate out the average rate of change, remember the average rate of change way a long time ago, chapter 1, section 4, the average rate of change can be given by the slope of the secant line. So I have our 2 points on our function here, and I can go ahead and graph our secant line. So here's maybe our secant line, the line that connects these 2 points for our function. And we need to find a place where f prime of c is equal to this. Well, remember, this is slope of secant line. Slope of secant line. Think average rate of change. Oops, forgot my A here. Average rate of change. And the derivative, this is the slope of the tangent line. That is the instantaneous rate of change. Instantaneous rate of change. And moreover, that c value should be in your interval. So our interval is here from 2 to 8, so that c value should be inside this interval. Now it's very important to have this kind of graphical understanding of what the mean value theorem is saying, because we don't have an equation for g, right? I guess, right, this is technically g of x, so let me go ahead. Really what we would have here, these would all be g's, not f's. So g prime of c, g of b, g of a, right? You're probably sitting there, what's f? Right? We don't have an f. It's a g this time. Okay, fair enough. So yes, we need to have this kind of understanding of what the mean value theorem says, because in this case we don't have an equation for g. It doesn't say g of x equals, right? If I had just g of x equals, I could go ahead and take the derivative of it, and then I could plug in c and I could figure it out. But in this case, well, since we don't have an equation for g, I have to understand what it's saying graphically. So okay, again, here's the slope of the secant line, and I want the slope of the tangent line to be the same as the slope of the secant line. Find me points where this holds true. And so you have to scan a little bit, but I think, for instance, right over here someplace, if you were to graph the tangent line here, the tangent line, I think you would get something like this. And I think that those two lines right there have the same slope, right? Because they're parallel. Remember, having the same slope means that the lines are parallel to one another. So I think one place where the slope of the tangent line is the same as the slope of the secant line would be somewhere around, right, maybe 2.5 or so. All right. Now in this case, right, it's asking for the c values that satisfy the mean value theorem. So we have to, it's not just find me one, but find me all of the c values that satisfy the conclusion of the mean value theorem. So this is one of them here. You may want to pause the video for a second. Try to find me, there's one more. All right. And I think it's somewhere right around 6 or so. So if you look here, right around 6, if you were to draw the tangent line, the line that just barely skims the graph at 6, I think that at this point right here, this tangent line is parallel to the secant line, based on my picture. So at 2.5 and at 6, so c equals 2.5 and c equals 6, satisfy the mean value theorem. And those are all of the c values, right, that satisfy the conclusion of the mean value theorem for this function. All right, so there's a good mean value theorem question. This one's nice, again, because there's no calculus to screw up, right? Because you don't have to really worry about messing up your derivative. Maybe there's a product rule or a quotient rule or something like that in your derivative, and if you mess that up, then kind of everything after it suffers, sort of deal. In this one, it's just, well, you don't even have the equation for g, so you have to understand what is this theorem saying. So it's a good problem because you can't mess it up, the derivative or anything like this, but if you don't understand what that theorem's saying, you're going to have a hard time answering it. All right, 3 examples down. Now we're to the long one. Example number 4, we're considering this function and we want to do a whole lot of stuff to it, right? Our end goal is to be able to sketch this function using what we know from parts A through D. All right, nothing to it but to do it. Let's get started. A, find the y-intercept and the asymptotes for our function, right? And so if you'd like to, you can either start up a graph now. I'm not exactly sure maybe what the range of our graph needs to be, how far to the left and right, up and down, all that sort of stuff. But we can go ahead and start collecting some information, right? Whenever we do a part, we can also do the graph down here. So the first thing it asks is find the y-intercept. That is, where does it cross the y-axis here? Where does it intercept the y-axis? So in order to figure out where does it intercept the y-axis, right, that's when x is equal to 0, right, that you don't move to the left or to the right any. Let me go ahead and put an A here. So in order to figure out where it intercepts the y-axis, why don't we go ahead and plug in 0 for x. So we're going to do f of 0, and so we get 0 plus 5 divided by 0 minus 2. And so we get negative 5/2. So that's negative 2.5. So that's saying that it's intersecting the y-axis down here. So if I went down 1, 2, 3, so it's going to intersect down here at negative 2.5. That's where it intersects. Okay, how about asymptotes, right? So that's the y-intercept. How about the asymptotes for our function? All right, so starting back in 1.5, right, we talked about vertical asymptotes. So vertical asymptotes happen most often when the denominator is equal to 0 and the numerator is not equal to 0, right? And we called these vertical asymptotes, we called them infinite discontinuities, right? They had a couple of different names. So let's figure out what does it take for our denominator to be equal to 0. So if we were to go ahead and take our denominator, set it equal to 0, that's saying when x is equal to 2. If you were to plug in 2 into the numerator, is that equal to 0? Do we have a 0 over 0 situation? No, right? So if you plug in 2 into the numerator, we would get, let's see, 4 plus 5, that's 9 divided by 0. So we'd have 9 divided by 0. This is a good indication that we have a vertical asymptote. So at x equals 2, we have a vertical asymptote. So again, I could go over here and maybe I could sketch at x equals 2, 1, 2 over, we have a vertical asymptote. So there is my vertical asymptote. The function's not going to be touching this line. All right, how about any other asymptotes? Well, okay, again, we look at our function here. The other asymptotes that we could have are horizontal or slant asymptotes. Remember, we had a very nice theorem in our video notes, right, that said if the degree of the numerator is 1 more than the degree of the denominator, so in here the degree is 2, here the degree is 1, then we're going to have a slant asymptote. So there is going to be a slant asymptote in this case, and so we need to go ahead and find out what this is. And the way that we find out what it is, right, we use polynomial long division. So let's go ahead and use some polynomial long division here. We're taking x squared plus 5, and we're dividing it by x minus 2. And we ask ourselves, what do I multiply by x in order to get x squared? Well, you would just multiply it by x. So if you take x and you multiply it by x, you would get x squared. If you were to take x and you were to multiply it by negative 2, you would get negative 2x. And then you go ahead and you subtract this away. So when you subtract it away, x squared minus x squared, well, that's going to be 0. Good. Good things are happening here. And if you were to take, well, let's see, there isn't any x term here. So really, if you want to, you can move this over, and you can write this as 0x plus 5. Right? So there's 0 x terms, and if you subtract away negative 2x, then I'm going to be left with positive 2x, right? Subtracting a negative. And then we go ahead and we move that 5 down, and we play the game one more time, and I ask, what do I multiply by x in order to get 2x? Well, that's going to be 2. So, okay, 2 times x is going to be 2x, great, and 2 times negative 2 is going to be negative 4, and remember we subtract this away. So 2x minus 2x, perfect, that's 0 x's. 5 minus a negative 4, that's going to be 5 plus 4, that's going to be 9. And remember, our theorem said that our quotient, our answer right up here, right, this is going to be our slant asymptote. So we do have a slant asymptote, and it's when y is equal to x plus 2. So y is equal to x plus 2. Let's go back over here and draw in our slant asymptote. So, okay, x plus 2, so it has a y-intercept of 2 up here, and it has a slope of 1. So if I go to the left 1, for instance, it goes down 1. If I go to left 2, it goes down 2. If I go to the right 1, it's going to go up 1. Here we're going to go right 2, goes up 2. So yeah, the slant asymptote is going to look something like this. Again, it's a straight line. You can see maybe I want more picture up here. We'll see. So it's a nice straight line. In this case, that line has right, a slope of 1 and a y-intercept of 2. Y equals x plus 2. All right, that was all for part A. Notice there were no derivatives or anything like this. Just intercepts and asymptotes here. Now we move on to, is the function even, odd, or neither? Even, odd, or neither. Remember, even, odd, or neither, this is kind of, it's an exploration of symmetry. And the way that you explore this is by computing out f of negative x. And so, in both cases, f of negative x, we're going to do this computation. And if this is equal to the original function, then it's even. If it's equal to not the original function itself, but the opposite of the original function, then it's odd. So again, both of these, they have to do with computing out f of negative x. So that's where we want to start. F of negative x. And so I'm going to go ahead back to our function here. Having a hard time remembering it. X squared plus 5. So x squared plus 5 divided by x minus 2. And notice, instead of plugging in x, I'm plugging in negative x. And so let's go ahead and try to simplify this as much as we possibly can. So negative x times negative x, right, that's negative x squared. That's going to be the same thing as x squared plus 5 divided by negative x minus 2. And so we compare this against, is this equal to our original function, right? Is this the same thing? Well, the numerator looks the same, x squared plus 5, but the denominator, unfortunately, right, there's this extra negative sign, right? This negative x minus 2. So this does not appear to be even, right? These are not equal. F of negative x, the numerator was good, the numerator was the exact same, but the denominator was off by a negative sign. Sorry, no luck. How about, is it equal to the exact opposite? Sometimes in order to see this, right, I like to do one more step and maybe factor out this negative. Right, so this would be negative times, in the numerator, I'm not factoring out a negative from the numerator, I'm just factoring it out from the denominator. So this question is this equal to the opposite of the function? So you can see I've kind of gotten this negative sign out here. So now we can just look inside of these parentheses and ask, is this the function itself? Oops, and you can see I made a small mistake here. It's x squared plus 5, x squared plus 5. There we go. So now let's go back and look at our original function. So again, the numerator looks good. X squared plus 5. Down here, x squared plus 5. This is perfectly lining up. How about the denominator? Here we have x plus 2. Here we have x minus 2. Darn it. So close. So the claim is this is not even and it is not odd. When you explore f of negative x, this is not the function and it's not the opposite of the function. And so when we go ahead and we sketch our graph at the end of the day, we'll see that it's not symmetric about the origin and it's not symmetric about the y-axis. And in fact, kind of this vertical asymptote, the fact that there was a vertical asymptote at 2 and not at negative 2, this is saying that it had really no hope of being symmetric, either even or odd. So what I'm saying here is, right, when you sketch your graph at the end of the day, you should definitely look at it and say, does it look even or does it look odd? Does it look like it has these symmetries? And if it does have these symmetries, then you want to go back You want to say, if your work in B did not conclude the same thing as what your graph looks like, you should try to figure out, okay, where did you go wrong? Because this is either an indication that your graph is sketched incorrectly or that you made a mistake in your symmetry calculations, right? And so this is a good way to catch any mistakes. All right, moving on to C. Again, no derivatives here. Finally, in C, it looks like we're going to need some derivatives, right? Find critical points. Use these to determine where the function is increasing and where it is decreasing. So, okay, I need to find critical points. Remember, critical points are points in the domain where either the derivative is equal to 0 or it's undefined. So let's go ahead, take our function here, and let's maybe calculate out the derivative. So f prime of x. The big thing here is that this is a quotient of two functions. So if you want to take the derivative, you're going to need the quotient rule. So let's go ahead and use the quotient rule. The derivative of the top is going to be 2x times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. And let's take a line to simplify. So 2x squared minus 4x minus x squared minus 5. It's in the numerator. In the denominator, I'll just leave this as x minus 2 quantity squared. And so we can see we do get a little bit of cancellation, a little bit of simplification here. Need a little bit more room. Right, so this 2x squared minus x squared, that's going to be x squared. And that's what our derivative is equal to. So x squared minus 4x minus 5, all divided by x minus 2 quantity squared. So let me go down here for C. Again, I've calculated out my derivative. F prime there we go. So, two things. When is this equal to 0 and when is it undefined? Well, you can see there's no square roots in this case, so the only place where we're going to have it's undefined is when you're dividing by 0. So what does it take for us to divide by 0? Well, x would have to be equal to 2. Now, is this a critical point? The claim is it is not, because x equaling 2 was not in the original domain of the function. Right? So if you had x equals 2, right, this is not in the domain of the original function. So this will not be a critical point, right? Because again, we actually have a vertical asymptote at x equals 2. So it's all connected, right? So okay, x equals 2 is out. It's not a critical point, even though the derivative is undefined, again, because it's not in the domain of the original function. So our only hope for critical points in this case is when the derivative is equal to 0. So let's take our derivative, set it equal to 0. Let's go ahead and get rid of this fraction, right? We're going to multiply both sides by x minus 2 squared. 0 times anything is 0. And so we get x squared minus 4x minus 5. And so, okay, how can we solve when a quadratic is equal to 0? And the claim is there's always three ways that we can use to solve these things. We can try factoring, you can try the quadratic formula, or you can try completing the square. The claim is when factoring works, it's the nicest. Otherwise, use the quadratic formula. Never use completing the square if you can help it. All right, so let's go ahead and try using factoring here. So sit here, stare at this for a minute, see if we can't factor it. I think we can. I think you can get an x minus 5 and an x plus 1. X minus 5 and x plus 1. I think that works out. If you FOIL this out, do you get back to where you started? Yes, you do. So at x equals 5 and at x equals negative 1, these are places where the derivative is equal to 0. Now, are they in the domain of the function? Well, again, the only place that's not in the domain of the function is at x equals 2. That's when you were dividing by 0. So yes, both x equals 5 and x equals negative 1 are in the domain of the function, so therefore these are going to be critical points. Well, they're critical values and they correspond to critical points. Okay, so we have a couple of critical points. Now we're going to go ahead and use our number line situation. Right? We're going to plot these things. We have x equals negative 1. we have x equals 5, and don't forget when you're doing your number line, you also plot down this x equals 2, this place where it's undefined. Even though it's not in the domain of the function, you can still switch at this point from increasing to decreasing, decreasing to increasing, right? You can have changes that happen here, and so it's important that you include it on the number line, even though it's technically not a critical point. Now we go ahead and we choose some test values. So for instance over here, maybe I have -2, test value between -1 and 2 is going to be 0, test value from 2 to 5 maybe like 3, and a test value that's larger than 5 maybe like 6. And we're going to plug these into the derivative, right? This is an exploration of the derivative because, again, we're trying to figure out increasing and decreasing. We're in part C right now. We're trying to determine where is the function increasing and decreasing. And remember, the derivative is all about the slope. If the derivative is positive, we have increasing. If the derivative is negative, we have decreasing. So we're interested in the derivative in these values. So let's go ahead, maybe back to my derivative equation up here. And if you were to plug in -2, okay, so if I plugged in -2, in the numerator here I would have 4 minus, and this would be 8, but it's -8, so this is going to be +8 minus 5, divided by -2 minus another 2, that's going to be -4, and you square it. So it looks to me that the numerator is going to be positive, and the denominator is going to be positive. So you have a positive divided by a positive, so on this interval the derivative is positive, and therefore the function is going to be increasing at this point, all right, on this interval. Let's try another one. What happens if I plug in 0? Well, if I plug in 0, it looks like I get -5 in the numerator, and in the denominator I'm going to have -2, but I'm squaring it. So I'm going to have negative divided by a positive. So negative divided by a positive, this is going to be negative. So on the interval from -1 to 2, we're going to have negative. Now see what happens at 3. If I go ahead and plug in 3 here, let's see, I'm going to have 9 minus 12 minus 5. And then 3 minus 2, that's going to be 1, and I'm squaring it. So in the numerator here, let's see, 9 minus 12 minus 5, that's going to be negative for sure. And then in the denominator, I have positive. So again, I have negative divided by positive, and you can see that this actually stays negative. Now again, that may not always happen, so you do actually have to consider it at 2, even though in this case it didn't change. And then finally at 6. So if I go ahead and I plug in 6, again, I'm plugging it into my derivative. I'm going to have 36 minus 6 times 4 is going to be 24 minus 5, all divided by, looks like 4 squared. Let's see, in the numerator, 36 minus 24 minus 5, that's actually going to be positive this time. And notice the denominator is always positive. That's the problem with when you square things. When you square them, they're always positive. So, okay, we're going to have positive here. Okay, our goal for part C was to try to figure out critical points. We did that, and then to figure out where is the function increasing and where is it decreasing. So f is increasing on -infinity all the way up to -1, then again 5 and after. So again, that's where the derivative is positive. When the derivative is positive, that's saying the slope is positive. We have an increasing function. So all the way up from -infinity up to -1. And then again from 5 and afterwards. All right, f is decreasing on the other intervals. So from -1 to 2, and then again from 2 to 5. That's where the derivative is negative. All right, what I usually like to do with these things is I go ahead and I kind of plot something over here on my graph. So we can see, for instance, at -1 there's a change. So at -1 there's a change, and I'm not going to do these in red, right? I was doing asymptotes in red. But at -1 there's a change. I'm going to do this maybe just in black, dotted line here. So over to the left of this we had increasing. And then over here we're going to have decreasing. And then all the way up to 5. So 2, 3, 4, 5. At 5, again, we make another switch. So I just put these kind of imaginary lines here just so I know that something's changing here. So it's decreasing. It was still decreasing from 2 to 5, and then after 5, we're going to start increasing. So this is how I just mark my graph in order to, when I have to go sketch the picture, I'm going to have all the information right here. Okay. One last thing, why don't we go ahead and do is actually map our critical points. So we had critical points at -1 and at 5. Let's figure out the function's height there, so that way we can go ahead and plug those in. So okay, the functions, we want f of -1. So now I'm not plugging this into the derivative anymore, I'm plugging it into the original function. So -1 squared, that's going to be 1 plus 5, divided by -1 minus 2. So this is going to be 6 divided by -3, so that's going to be -2. So the function's height at x equals -1 is -2. So down here. That probably makes sense. It should probably be close to the Y-intercept, which is around -2.5. All right, and then how about f of, our other critical point was at 5. So f at 5. So again, we take 5 and we square it. That's going to be 25. Add 5 to that. And then we have 5 minus 2. So I'm going to have 30 divided by 3. So this is going to have a height of 10 in this case. So I know you see that maybe I didn't have enough room in my graph, but okay, let's go ahead. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So over here, for instance, this is where we're going to have our other critical point. All right, and that is part C. Again, we're going above and beyond because we know we're going to have to sketch this here. Right? It didn't actually say find the heights of these critical points and whatnot, but again, if we want to sketch this, we're going to need that information. All right, so finally for part D, we want to find the inflection points for f of x and where it is concave up and concave down. So inflection points, remember, this is an exploration of the second derivative. So increasing, decreasing, that's all about the first derivative. Inflection points, that's all about the second derivative. And we can use that information to figure out where we have concave up and concave down. So the first step here, let me go ahead and use some room over here for D. The first step is going to be to calculate out the second derivative. That is the derivative of the derivative. So let's go back to our first derivative, and you're going to need to calculate out the derivative of this. So go ahead, pause the video, try to get as far as you can. I'll do the same thing, and then we'll go ahead and talk over the answer. All right, this is as far as I get before I want to talk to you really quick about there's a nice trick here with this one. The fact is you have so many of these x minus 2's. Again, I was using the quotient rule. I took the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. And you can see I have so many of these x minus 2's. So this term up here has 2 of them. This term right here only has 1. In the denominator we have 4. So we can go ahead and divide out at least one of these across the board, right? So this one has 1 x minus 2. So we can go ahead and cancel 1 x minus 2 from the numerator. So across both terms in the numerator with one of them in the denominator. And that's going to make this a lot more reasonable to actually expand this all out. So now if we go ahead and FOIL in the numerator, right, so I'm going to have 2x times x, so that's going to be 2x squared minus a 4x minus another 4x plus 8 minus x squared, oops, I forgot this 2 right here. So minus 2x squared. Right, so all of these are going to have this 2 and they're going to have this minus. So okay, when I apply that to x squared, I get minus 2x squared. When I apply that to negative 4x, that's going to be plus 8x. And when I apply that to negative 5, that's going to be plus 10. And now we just have x minus 2 cubed in the denominator. And so we can see actually there's quite a bit of cancellation that happens here. 2x squared, negative 2x squared. These two together make negative 8x. Well, we have a positive 8x. So those cancel out. And so after all is said and done, I know it looked like a monster of a problem, but it actually simplifies down to something relatively nice. And that is just 18 divided by x minus 2 cubed. And now in part D, we're interested in inflection points. That's when is the second derivative equal to 0, or when is it undefined? Again, it needs to be in the domain of the original function. And so, okay, this is undefined when x is equal to 2. But again, this is not an inflection point because it's not in the domain of the original function. Okay, well, what would it take in order to make this second derivative equal to 0? Well, we'd have 18 divided by x minus 2 cubed. What does it take in order for that to equal 0? Well, again, let's go ahead and cross multiply, and we would get 18 equals 0, and we say, oh crud, right? There's no way that 18 equals 0. And so the conclusion is that there are no inflection points. There's no place where you can make the second derivative equal to 0. No matter what you do, no matter what x value you choose, it's never going to be equal to 0. So there are no inflection points. Oops. Inflection points. Still, we need to go ahead and look at our number line to map concavity. So, okay, concavity. This is all about the second derivative here. Even though there are no inflection points, we did have a place where the second derivative was undefined, and that's at x equals 2. So even though it's not an inflection point, we still have to go ahead and map it on our number line. So now let's go ahead and choose some test values. So for instance, maybe 0 over here, and maybe 3 over here. And why don't we go ahead and plug that into our second derivative. So if I go ahead and I plug in 0, I would get 18 divided by negative 2 cubed. Well, it's going to be a positive. Divided by negative 2 cubed is going to be negative 8. That's certainly negative. So over here we have negative. That is concave down. After 2, well, we have, let's see, 3. If I plugged in 3, I would have 18 divided by 3 minus 2. That's going to be 1 cubed. So I have a positive divided by a positive. So this is going to be positive. So you can see that, yes, it was important that we had this 2 here because there was actually a change, right? It went from negative to positive. And so our result is that f is concave down on the interval from negative infinity all the way up to 2. And then f is concave up on the interval 2 and larger, or strictly larger than 2. All right, so now I've done all the parts for D. Let's go ahead and also map this information onto my graph. So on this first interval here, right, it was concave down. So I'm just going to do and I'm going to do an arrow down. And that continued all the way to 2. So this was decreasing here. It was still concave down. And then after x equals 2, that's when you switch and you have concave up. Concave up. All right, and again, so kind of these black little dotted lines, and along with my vertical asymptote, that's where things are making changes. This is where I have to be careful. All right, so all of this information, A, B, C, and D, right now we want to take this and combine it into a sketch for a function. So let's go over here, and maybe let's start at the far left-hand side. We have the function is increasing, and it's concave down, and we have the slant asymptote. So as it goes off to infinity, right, we want to be getting closer and closer to the slant asymptote. And I know that I want to contain these 2 points right here. So we also know that it's increasing and concave down. That's good. So let's see. It's getting closer to the asymptote over here. It's increasing. It's concave down. So right, the slope is decreasing here. Decreasing. Right. So now after this point here, right, we switch from increasing to decreasing, but it's still concave down. So still concave down. We have this kind of bowing downward. And remember, we have a vertical asymptote. So it's getting closer and closer to this vertical asymptote. It's getting more and more negative. So okay, that's the first part of our function here. It gets close to our slant asymptote. That's a good thing. It contains these 2 points. Look, on this first interval, it's increasing in concave down. Great. And here it's decreasing in concave down. Great. And then it gets closer to this vertical asymptote. So I think we've mapped it, and it's hit all of our the things that we wanted it to hit. All right. Now on this next interval, after here, well, we want it decreasing and concave up. So if I was to start after the vertical asymptote, if I was to start it down here, right, there's really no place for it to decrease to, right? Again, it's in one of these infinite, vertical asymptotes here. So let's go ahead and make it flip up, and let's start it maybe up here or so. Now we can decrease and it'd be concave up. And notice, we want to hit this point too. This was another one of those critical points. So decreasing and concave up, so that means it's bowing upward. So maybe something like this. And then after this critical point, it's increasing and concave up. And remember, we have this, slant asymptote here, so that we want to get closer and closer to. So now it's increasing and concave up. And we want to get closer and closer to this slant asymptote. So maybe something like this. Again, maybe I'll extend my vertical asymptote a little bit. Slant asymptote. There we go. So yes, this is decreasing here. As you move from left to right, it is getting smaller. It's concave up. It's bowing upward. Increasing concave up. I got that here. That's good. And then let's see. It's getting closer to my slant asymptote, and it got close to my vertical asymptote. So this seems to be a pretty darn good picture. And now we can look at it one last time and say, is this thing symmetric about the origin? No, right? And so therefore it is not odd. Our conclusion was good here. It shouldn't be odd. Is it symmetric across the line, x equals 0, the Y-intercept? If you were to flip this, right, flip this across the y-axis, would you have the same picture? Absolutely not. So therefore it is not even. So this is how we can use the picture that we get at the very end to make sure that our conclusions, about symmetry are correct. All right, I know this was a very long problem. These curve sketching ones are quite long, but they are also quite important, right? If you were to survey a bunch of mathematicians and you say, what are the big ideas in Calculus 1? Pretty much everyone would come back and say related rates, optimization, curve sketching. So we've done related rates. That was 2.8. Here we are doing curve sketching, very important. And then finally optimization, that's going to be 3.7. So that's going to be in next week's stuff. So yes, even though it is a long process, it is very important. This is some worthwhile pain, I guess, right, to go through this process. All right, thank you very much for watching. I'll see you next time.